All right. And again, this time we're switching to OQCAM. All right. So let's begin by uh, defining in section 5.1. Again, remember section 5.1, a lot of this section is the review of either pre-calc or if you had calc 3, it's the early part of calc 3 stuff. So let's begin by talking about the length and dot product in Rn. First of all, the length. So let's do that. This is a definition of the length of the vector. The length of a vector and whatever the vector may be, v, u, w, we're going to look at the length in Rn. Now, the length of the vector also, aka, also known as the norm of a vector. So a length or norm of a vector. And suppose our vector, I'm just going to write it in general form. Suppose we have an n-dimensional vector. So vector v, the components are the scalars v1, v2, dot, 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 all the way to vn. So I have some n-dimensional vector. Okay, this is a vector in Rn, in an n-dimensional space. So the length of the vector is simply the magnitude or the norm of the vector. And there you go. I'm going to use double, it looks like double absolute value lines, and that's what it looks like. In a way, it is an absolute value. You can think of this as an absolute value because the length of the vector is positive. So maybe that is the motivation for the symbol, the absolute value symbol. And then here, how you find the length of the vector is you add some of the squares of the components of the vector. And there you go. So this is going to be the length of the vector for us. Now, because length is just like in any geometric shape, in geometry, length, area, perimeters, volumes, these are all positive quantities. So the length of the vector, therefore, is going to be a positive quantity for us. The smallest number, the lowest value for v, is going to be 0. And that's when you have a zero vector. Okay, so that's that. And indeed, for a zero vector, the length of the vector is going to be 0. Now remember, the length is a scalar quantity. Okay, in other words, it's a constant, it's a real number. So here I have a vector 0. For zero vector, the length is 0. Okay, now we talked about the standard basis for Rn. So let's write that the standard basis for Rn, each vector has a length 1. Okay, each vector has length 1. And I'll write them down for you in just a moment. So here the standard basis is going to be the standard, we're talking about unit vectors here, standard unit vectors. Unit vectors. And in R2, for example, in R2, our unit vectors are ij vectors, right? We've talked about those before, the ij vectors. And these vectors, if you remember, vector I was vector 1, 0, and j is 0, 1. All right, so the length of this vector, each of these, this is going to be 1. And the length of this will be 1 because you square 1 plus the square 0, you get 1. Square root of that is 1. Same thing with this one. Now in R3, our standard basis vectors are ijk. And remember, that's by basis, we're talking about a vector space here where every other vector could be written as a linear combination of ijk. Okay, so that's what it is in ijk, and this one has 3 vectors. This one is 1, 0, 0. The j vector will be 0, 1, 0, and the k vector is now 0, 0, 1. And again, each of these vectors are unit vectors of length 1. Okay. And if you have any questions, by the way, please ask. Feel free to interrupt and ask. All right. Now, often we talk about vectors that are parallel. So what makes two vectors parallel? So suppose I have two vectors, u and v. These two vectors are parallel. That means they either go in the same direction, right, or in opposite direction. So symbolically, that means we can write one vector as a constant multiple of another vector. So that's the definition of parallel vectors for us. So you can either write u as a constant multiple of v, or you can write v as, I don't know, let's call that C1. V would be C2u. Again, all I'm trying to say here is that one is constant multiple of the other. One is constant multiple of the other. So that's what that symbol means. Now, if C is positive, if the constant multiple of the vector is positive, then the two vectors will have same direction. The two vectors will have the same direction. They go in the same direction. So let's say this is going to be vector u, and this is vector v. That's going to be twice u, 2u, and that is vector v. Okay, now if you notice for this vector, they go in the same direction, and 2 is positive here. So that's indicative that vector v goes in the same direction. Now, if C is less than 0, then they go in the opposite directions. Opposite direction. And in this case, for instance, let's say here's a vector u, and vector, this would be negative 1/2 u. So that's my vector v. It's half the size of this larger vector. If this is u, this vector v would be half the size. The coefficient is negative, so that means it's going in the opposite direction. Now, when it comes to vectors, by the way, the idea of parallel, two vectors could be, again, parallel going in the same direction. So I have these two vectors are parallel, right? Here's vector A, and this is vector B. So I have two vectors that are parallel, and in this case, again, going in the same direction. Or they could be parallel going in the opposite direction. So here's vector A, and this is vector B now. You see that? They're going in the opposite direction. And because you can translate vectors, right? We can translate them from one location to another location. So I can actually think of these two vectors, A and B, would be this one. So A is the longer. Let me actually do this. The longer of the two. The longer of the two vectors. Here, this is A and this is B. Notice it looks as if B overlays on top of A. So I can say these two are parallel, even though it looks like they coincide. So because one is directly above the other one. Or they could be going in the opposite direction. So these two vectors are parallel also. There you go. Parallel going in the same direction, parallel going in the opposite directions. All right. Now, let's talk about the length of a scalar multiple of a vector. Let's talk about that. So this is actually a theorem. Okay, a theorem in your book. So this would be, I believe it's theorem 5.1. Okay, this one, the length of a scalar multiple of a scalar multiple of a vector. And for this one, we're going to say, well, let's suppose we have a vector v. This is in Rn. Okay, in Rn, and suppose we have scalar c. And c would be a constant, if you will, or a scalar. Now, the magnitude of CV, that would be the scalar multiple of V, is going to be absolute value of C times, and we will prove this in just a moment, magnitude of V. There you have it. Now, the need for absolute value, by the way, remember the magnitude of a vector is always positive, lowest is zero. So if C is negative without absolute value, this would imply the length is negative, and that kind of defies the definition of the length of the vector. Okay, so how do we prove this one? The proof is actually pretty simple. So if I write the constant multiple of the vector CV as CV1, CV2, dot, 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 all the way to CVN, that's just a constant multiple in vector notation. And suppose we want to find the magnitude of CV here. So what will the magnitude be? That's when you square each of the component, right? So it's going to be CV1 quantity squared plus CV2 quantity squared plus dot, 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 all the way up to the last one, CVN quantity squared. And then we take the square root of that, right? Which, if it's okay with you, I'm going to write it to the 1/2 exponent. It's the same as a square root, right? Square root of x is x to a half. So I'm just using that notation. Instead of square root, I'm writing it to a half exponent. Now, within the bracket, because you have the same constant, CV1 squared, CV2 squared, these are the same constant. So you can square within each of these, so you get C squared, dot, 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 C squared. Every element, every component, every term in the bracket will have C squared in it. So we can actually, now let me go back to square root here. So it's going to be C squared, and then as a factor, and then you get V1 squared, V2 squared, plus dot, 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 plus V sub n squared, right? Now, this time, because we have product, we have a factor multiplied by another factor, we can actually take the square root of each of these factors. That comes from the multiplication rule of radicals, right? As long as one of these radicands are positive, and we know C squared is positive, we can write it as product of two radicals. So this is going to be simply square root of C squared times the square root of V1 squared, V2 squared, plus dot, 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 plus Vn squared. Now, square root of C squared, this would be absolute value of C. And again, that comes even from algebra. Remember, square root of x squared? If x could be any real number, that's going to be absolute value of x, right? We know that from algebra. If x is allowed to be a negative number. And the constant c here, the scalar, is a real number, right? Could be negative. And there you go. Within the radical here, that's simply the magnitude of the vector, isn't it? And there, that proof is complete. So that's simply the length of a scalar multiple of a vector. All right. Now, we have another theorem here. Let's look at this other theorem. This theorem is for unit vector in the direction of v. Unit vector in the direction of v. Okay, this one. So for this one, suppose we have a non-zero vector. Okay, if v is non-zero, a vector in Rn. So it could be an n-dimensional vector like the one above. If that's the case, then we're talking about a unit vector. That's a vector of length 1, and we want it to go along the same direction as v. Then this unit vector is given by a vector v divided by magnitude of vector v. So this is going to be, this is a unit vector in the direction of v. And there you have that. Now, the proof of this one, again, is fairly easy, straightforward. So for this one, let's say if we want to prove it, then proof is going to be, well, the magnitude of the unit vector is 1, right? So we can write this as the magnitude of vector v over the scalar. I'm going to let the scalar be magnitude of v. Remember, this is a scalar. So I'm looking at the magnitude of vector v divided by scalar. And because the denominator is a constant, it's a scalar, we can actually bring it outside and write it as 1 over magnitude of v, because this is a constant, and take the magnitude of this vector. Well, the magnitude of the vector just itself is that. And at this point, we have two scalars that look exactly the same. We can actually cross these out. We can cross them out because we are not crossing out a vector, we are crossing out its scalars now. And that's going to be 1, and that's what this theorem calls for. Okay. Now, the process of finding u, when we try to find a unit vector in the direction of another vector, it's called normalizing. So let me just note this. When we say to normalize a vector, normalizing vector v, what do we mean by that? That means find a unit vector in the direction of v. There you go. So that's what normalizing a vector means. Okay. So hopefully everybody's good at this point. Now, instead of going through all of these in the interest of time, so we don't spend too much time on this, I'm going to switch our my share to, let me go to something else. I'm going to share the book with you now. So I'm going to change my share to the pages of a book. So this way it will go a little faster. Again, all of these are in this section. So we started by talking about the length of the vector. So hopefully you can see now what's on my screen. So figure 5.1, this is a vector. It's a position vector, in fact, because it starts at 0, 0. The components of the vector, scalars are v1, v2. The magnitude of the vector is that. Now remember, in the book, he uses boldface. All books use boldface to show a vector quantity. So all of these boldfaces are vector quantities. Something that's not bold is a scalar. And in my notes, if you notice, I put arrows on top of the vectors. So because I cannot boldface them, it will just take a long time to do it. So it's much easier just to go with just to go with the arrow on top of the vectors. Okay, so we talked about theorem 1, we talked about theorem 2, and we will look at exercises ourselves in a moment. The next idea here is distance between two vectors. So suppose we have vector u, vector v, and by distance, it's like, what is the distance between two vectors? We're talking about the distance from tip to tip. That's what the distance between the two vectors is. It's the tip-to-tip distance between two vectors. So how do we find the distance here? Using distance formula in algebra. That formula should seem familiar to you. We use x1 minus y1 squared plus x2 minus y2 squared in algebra. Sorry, x1 minus y1 quantity squared plus x2 minus y2 quantity squared. So it's the same thing, except the components are u1, u2, v1, v2. And there you go. This will give us the distance between them. Now, because distance is a length, it is a length, a distance between two vectors. So we can show that using the magnitude or scalar, u minus v. We can show that. And that would be the distance between two vectors. Now, properties, if you will, of distance between two vectors. The distance, because again, it's a geometric measure, it's always going to be at least 0, right? The distance is positive. In other words, we don't have negative distance. And the only time the distance between two vectors is scalar 0 is if two vectors are equal. They must be identical, then the distance between them is 0. Otherwise, it's not 0. And the other thing is the distance between UV and VU is the same thing. The distance between two vectors. Whether you find distance between U and V and U, those are the same. Okay. Now, and again, we'll look at the exercises in a moment. We do our own exercises. The next idea that we will extend to the next section when we talk about inner product spaces is the dot product. So the dot product, then here's the definition of dot product. It's down here in the box, the definition of dot product. The definition is that suppose you have two vectors, u and v. The dot product is also called the scalar multiplication or inner product. So inner product, scalar multiplication, or simply dot product. That's when you multiply each component, like here for u is u1, you multiply by the corresponding component in the second vector. So there's your first term in the sum. And then you look at the second component in the vector, look at the second component in the other vector, multiply those together, and that's what you get down here. So if we do that for every components of the two vectors and add them up, simply sum those up, then that's called a dot product. The dot product is a scalar, it's a real number. The result is not a vector. And dot products, by the way, are quite useful. A lot of times, for instance, let's say, what do we use dot product for? You may have seen this in your physics classes, for example, work done by a force acting on an object is the dot product of force times distance. So in a way, the dot product, what it does, it projects the components of a vector onto another vector, and it multiplies the corresponding units. So in the case of force, for instance, you can look at force in the x direction and times movement in the x direction plus projection of force in the y direction times the movement in the y direction, and that's going to be useful. So that's typically how it's used in the engineering courses. Now, what are some of the properties of these dot products? You can see these properties here. Dot product is commutative, so that's number one. Property number one says dot product is commutative. So whether you do u dot v, v dot u, it's the same product. And remember, this is a scalar product. So every one of these numbers, 1, 2, 3, 4, 5, the result will be scalar. Dot product is distributive. You can actually distribute u dot v plus w. You can distribute u to v, and then you can distribute u to w, and then separately, and then add them up. Scalar multiple of a dot product, you only distribute the scalar c times one of the vectors. So you don't distribute the constant to both vectors. You can distribute the constant to u, or you can distribute the constant to v, but not both. So that is the scalar multiple of a dot product. Number 4, any vector dotted with itself. That's what this is, v dot v. Any vector dotted with itself gives you the magnitude of the vector squared. Okay, so that's what that one is, property number 4. And lastly, number 5. The dot product of any vector by itself is at least 0. It's 0 or more. Now, the only time the dot product of a vector with itself is 0 if vector v is the 0 vector. 0 vector dotted with itself is 0. Otherwise, it's going to be positive. It will be positive. Okay, and remember, number 4 and 5 kind of go together. V dot v, number 4 says the dot product of a vector by itself is positive, at least 0. And this one, v dot v, is magnitude of v squared. So you can see the right side of this equation, it will be positive. Okay. Now, let's see. So these are just some of the exercises or examples on properties of dot products. Now, let's say we want to find this time the angle between two vectors. Okay, we want to find the angle between two vectors. So how are we going to do that one? Um, well, let me see the angle. Maybe it's a little early. We'll do that in just a moment following this next theorem. Theorem 5.4 is the Cauchy-Schwarz inequality. Okay, so for the Cauchy-Schwarz inequality, we have two vectors, u and v, vectors in Rn and dimensional vectors. Then the dot product, notice we have absolute value of dot product because dot product could be positive or it could be negative, right? The dot product of vector with itself, let me go back up here, with itself is positive. But in general, if you do dot product of any two vectors, the dot product could be negative. So for that reason, you take the absolute value. So the Cauchy-Schwarz says that if you do a dot product of two vectors, that product would be, the absolute value of the product would be less than or equal to the magnitude of the vector times the magnitude of the second vector. So that's what the inequality is. And the proof is there, by the way, if you are interested in the proof of this theorem. So this is something we will note later on in another theorem. We're gonna take advantage of this theorem later on in another theorem. Okay, in the following what you call it section. So we're gonna come back to Cauchy-Schwarz later on. And let's see. So everybody's okay, I hope. Again, please feel free to ask questions, folks. Otherwise, I just gather you're fine. All right, so there's your Cauchy-Schwarz inequality. And now we're talking about the angle between two vectors. Now let's talk about this one. So first of all, the angle between two vectors is defined as following. Notice this doesn't give you theta. This gives you this formula definition. It gives you the measure of the cosine of the angle, not directly the angle. So to find the measure of angle theta, we have to go to the inverse trig function, right? The arc cosine or inverse cosine in order to find theta. And we're going to stay, for theta, we're going to keep it from 0 to pi, right? Which is the range of inverse cosine. So we're going to keep that theta from 0 to pi. So this way we get unique values. And the formula is u dot v over magnitude of u over magnitude of v. Okay, now let me see. I'm not sure if he proves this. No, he doesn't. So it'll be interesting to see just the proof of this one, why this works. Yeah, this one. So let me switch to my OQ cam here. And I'll show you a proof of this one. So we want to prove the formula that you saw earlier. Okay. So we want to find, let's say we want to find the cosine, or I'm sorry, not the cosine, but the measure of the angle between two vectors. Now, I'm going to draw them like this. Suppose this is vector u. Okay, and then I have another vector. Let's call this vector v. And the angle between them is what theta is. Okay. Now, if I connect from the tip of u to the tip of v, this vector is going to be vector v minus u. Okay, that is vector v minus u. Now, how do I know that's vector v minus u, not u minus v? Let's show that one. So suppose this is vector v. And vector u is this one. And let's say I want to find the vector v minus u. I want to see what that vector looks like. So in order to do v minus u, remember to subtract a vector, we add a vector in the opposite direction to v, and that's going to be v minus u. Well, opposite of u, that means a vector that's going to go in this direction. All right, the negative u is going to change the direction of that vector. Right, so this is now a negative u. And then we want to add these two vectors together, and we can use the parallelogram method to do it. So here's vector negative u, right? This is vector negative u, and this is vector v there. Right? And then if I draw the diagonal, that's going to be the sum vector, correct? That's going to be this vector. It's going to be the sum of a vector v plus negative of u. So it's going to go in that direction. You see that? Now, because we can translate vectors, so I can translate it instead of this, which means pretty much cut and paste. That's what translation is. It's a cut and paste job. So I can cut it here and paste it up there. It's going to be exactly the same vector, going in the same direction, having the same magnitude. So this is going to be the vector v minus u. You see that? So that's how I knew this vector is going to be v minus u. If you go from the tip of u, vector u, if you go from the tip of u to tip of v, then you're doing v minus u. If you change the direction, by the way, so let's say this is u and this is v now, same thing I started with. If I change the direction, if I go from v to u, sorry, there you go. If I go from v to u, this one, that's going from v to u now, right? So this is going to be u minus v. That's what that is. So going from u to v is v minus u. Going from v to u is u minus v. Now, I'm gonna do this one for the proof of the angle between two vectors. Now, looking at the original one I have, this one, the top one. If you recall the law of cosines from trigonometry, the law of cosines says that in a triangle, you can write the square of one side is equal to sum of the squares of the other two sides, negative twice the included angle. All right, twice included angle, and then times the length of the two sides. And in other words, here's the law of cosines. There's, depending on the size you're looking at, so the law of cosine goes like this. It's like a squared is b squared c squared. Hopefully this resonates with most of you. Negative twice bc cosine of included angle theta. Okay, that's the law of cosines. So we're going to make law of cosines work with our triangle here. Therefore, the magnitude of vector v minus u, that would be the side of this triangle, right? Squared is equal to the magnitude of u squared plus magnitude of vector v squared. Negative twice the product of the magnitudes. This is the law of cosines right now we're looking at. Cosine of included angle. Okay. Now, the left side, remember we had a property of the dot product. That's, which one was it? We said v dotted v. Remember, this was a property of dot products. V dot v gives you the magnitude of vector squared, right? This was one of the properties of dot product. Well, on the left side, I have magnitude of the vector squared. So we can actually rewrite the left side as the dot product of v minus u by itself, right? So I can write it as v minus u, this vector, dotted with itself, v minus u, right? That's the left side. And let's continue. I'm going to put ls. That means this is the left side. So what is the dot product? Using properties of dot product, we can actually distribute. This is going to be v dot v. And then it's going to be minus v dot u, correct? Minus u dot v. I'm foiling it, if you noticed here. First, outside, inside, and then last. The last is going to be negative times negative is positive. Positive u dot u. And there you have that one. So that's just the left side, folks. The right side, I'm leaving it alone. Now, v dot v, we just said using the properties, that's just magnitude of a vector v squared. V dot u dot v, remember dot product is commutative. So v dot u dot v is the same scalar. So I have twice u dot v or v dot u, doesn't matter. So it's twice that. And then u dot u also gives you the magnitude of u squared. Okay, now we have that one. And so let's just say this is the left side. Now we're going to equate the left side and the right side, right? Remember, this is the left side and this is the right. So on the left, we have magnitude of v squared. Okay, magnitude of v squared minus 2, the dot product, uv, plus magnitude of u squared. And on the right side, we have 1, 2, 3 terms. That's magnitude of u squared plus magnitude of v squared, negative twice magnitude. I'm just copying, folks, up here. 1, 2, 3 terms. I'm copying them down there. And my note, cosine theta. That's the left and the right side. All right. And then what we can do is, now we can cancel terms, like terms on either side. Magnitude of v squared, the v squared cancels. Magnitude of u squared on the right, u squared on the left cancels. And then at this point, you can divide both sides by negative 2, because I only have one term left on this side. Divide by negative 2. What do we get? We get u dot v is equal to magnitude of u, magnitude of v, and then cosine of included angle. And then we can solve for cosine theta. That would be u dot v over magnitude of u and times magnitude of v. And there you go. So that's the proof of that formula that he left out. Okay. So in order to find, again, theta, we need to find cosine of theta in this case. Now, let's see. And you can prove, by the way, because remember, sine and cosine are range bound, right? Isn't cosine theta between -1 and 1? Agree. This is from trigonometry. We know that the cosine and sine, the same thing. Cosine and sine are range bound. So this would be the graph of cosine, for instance. Right? The max is 1, the minimum is -1. And that's what this says. Well, we can show that this expression is going to be between -1 and 1. This expression on the right. How do we know what's on the right between -1 and 1? Well, we know from, let me just put this as a note. We know by Cauchy-Schwarz, right? From Cauchy-Schwarz inequality, we looked at that in the previous, on the previous page, we saw this. Cauchy-Schwarz says the absolute value of the dot product is going to be less than or equal to the magnitude of u times magnitude of v, right? This is from Cauchy-Schwarz. Cauchy, and then we have by Schwarz. inequality. Well, in here, if you divide both sides by magnitude of u, magnitude of v, we get absolute value of u dot v divided by the right side, magnitude of u, magnitude of v is going to be less than or equal to 1 when you divide both sides by the right side, which is a scalar. Now, we can rewrite absolute value inequalities just like we did in algebra. Let's look at the analogy to algebra. If you recall from algebra, when we have absolute value of x less than or equal to k, in algebra, they told us we can write this as x between negative k and k, correct? That's from algebra. Therefore, because I have absolute value in the numerator, we can rewrite this expression. Remember, denominator is just a scalar, it's positive, so we can ignore it for now. So I can write just the absolute value between 1 and negative 1 using the inequality. So that means that this time without the absolute value, notice in our algebraic expression, this expression doesn't have absolute value on x. So this is just going to be now u dot v over magnitude of u, magnitude of v. Right? And that's going to be between negative 1 and 1. But then this is the formula for cosine theta. So you can see that we can replace it now for cosine, and the last statement is established. We take that to be truth. We know that already. Therefore, the statement prior to that has to be true. So, in other words, we are guaranteed in this formula, the right side of the formula is going to be between 1 and negative 1. This is in case somebody had doubts. Like, will that ever happen? Will that ever happen that it's not between 1 and negative 1? No, it can't. Now, a few other notes here about the angle between two vectors. If the dot product u dot v, because remember the denominator of that formula is magnitude of u, magnitude of v, those are always positive. So whether that fraction is negative or positive depends on the dot product. If the dot product is negative, u dot v is negative, less than 0, then that would mean that theta has to be between pi over 2 and pi. Remember, cosine is negative in the second quadrant, right? And that's why theta would be in the second quadrant. This means theta belongs to second quadrant, Q2. Okay, that's if the dot product is negative. What if the dot product is 0? If the dot product is 0, that means cosine is 0, right? Well, in 0 to pi, cosine is 0 only at 90 degrees. True? So theta must be pi over 2 because, again, cosine of pi over 2 is 0. And if the dot product is positive, u dot v is greater than 0. And that means the angle is in the first quadrant, correct? Cosine is positive, so that means theta must lie between 0 and pi over 2. And there you have that one. Now, if theta is 0, notice I don't have 0 in here. Then none of these theta is 0. 0 is right there, but it's greater than 0. If theta is 0, then u and v will have the same direction. In other words, the angle between them is 0, right? I'll do the geometry of that one for you. So here's how the angle between them is 0. This is vector u. Okay. And then another vector v will go like that. You see how that goes? This is where theta is 0. They're going in the same direction. If theta is pi, again, the dot product is 0. If theta is pi, of course, there are What do we know about it? The angle between them is 90 degrees. So that means the two vectors, the angle between them is 90 degrees. So that means the two vectors are orthogonal. And we'll get to that one in a moment. So that means they're perpendicular to each other. What if theta is pi? And this, now we cover the entire spectrum from 0 to pi, including the endpoints. If theta does equal to pi, then in this case, u and v have opposite direction. They have opposite direction. So that means, for instance, if this is vector u going on the right, vector v has to be going in the other direction. This is going to be vector v. To where the angle between them, see, that's 180 degrees, or pi. For the one I have here, the angle is 0 because they're going alongside each other. So again, hopefully everybody's okay on that one. So we can actually now define orthogonal vectors. So this would be the definition of orthogonal vectors. So we're going to say two vectors are orthogonal, u and v in Rn. N-dimensional vectors are orthogonal. Again, orthogonal means perpendicular. They're orthogonal when the dot product is 0, scalar 0, remember? Because dot product is always scalar product. And there you have it. And that's what we said up here as well. All right. So hopefully everybody's good on this one. Any questions so far, ladies and gentlemen? Is everybody okay what we're doing? Hopefully it's not too complicated. Is everybody good? Okay. Let's continue on. So let me switch back to the page of a book. And we are over here now. Okay, so we did go through the angle between the two vectors. And these are, again, all the possibilities that I just put on the paper. Here's opposite direction. This one, the vector is between pi over 2 and pi, because cosine theta is less than 0. Cosine theta 0, they're orthogonal, greater than 0 in Q1. Theta 0, they go in the same direction. Theta pi, they go in opposite direction. Okay, and almost done with this section, folks. Now, theorem 5.5, this is another theorem. This time is actually, this is now triangle inequality. So we talked about Cauchy-Schwarz. This is triangle inequality. The triangle inequality says the magnitude of the sum vector is going to be less than or equal to the sum of individual magnitudes of the two vectors. Okay, so there's no way the magnitude of the sum vector will be greater than the individual sum of the vectors. And the proof of this, again, is in the book. You're looking at it in front of you for those that are interested. So far we had Cauchy-Schwarz, we have triangle inequality, and we're going to wrap it up with Pythagorean theorem now. Now we all recognize Pythagorean theorem from geometry, right? In a triangle, we have in a triangle that has 90 degree, a right angle triangle, a right triangle they call it. The sum of a square two sides equal to the square of the hypotenuse. Well, this is kind of similar to it, except with vectors. The sum of squares of two vector is equal to the vector sum squared. And that's as close to Pythagorean you come as we do in a right triangle. And there you have it. So we have, again, Cauchy-Schwarz, we have triangle inequality, and we have Pythagorean theorem. And the last thing here that you're going to see is the dot product and matrix multiplication. It is possible to write matrix multiplication as dot product, but here's the thing. This is a row vector. U is a vector here. Okay, the way it has it. Now in Rn, it has n rows, one column. So it's actually a column vector, but they write it like this, which could be misleading. This looks like a row of a matrix. But as a vector, it's going to be like a column vector here. So U is a column matrix because it has one column. A V also has one column. Well, the way it is, we cannot multiply these together, right? Because U times V, if you want to multiply, this is n by 1 times n by 1, right? The inside numbers won't match. N by 1 and n by 1. The inside would be 1 by n, but the outside numbers don't work. So anyway, it's impossible to multiply them using matrix multiplication. So if we want to, one way we could multiply them is to transpose U. This column vector, when it's transposed, is going to look like this, right? N rows, one column transpose becomes one row, n columns. And now we can multiply a 1 by n, multiply by n by 1. The inside numbers are n. The final product is going to be a 1 by 1, which means a scalar. So you multiply u1 times v1, and you get u1 v1. Then you multiply u2 v2, you get that product, and so on and so forth. So that's how we can multiply those two matrices using dot product. You have to use U transpose in order for this to work. Okay. And that's about it from this section. So before we do the exercises, folks, any questions, ladies and gentlemen, any questions about anything we've done so far? Everybody's okay? No problems? Anyone? Okay, if no question, then let's take a look at some of these exercises together. So I'm going back to the page of the book, and I'm going to try to do ones that are similar to your homework problems. So for instance, let's take a look at, the first 8 problems are pretty simple, straightforward. You want to find magnitude of the vector. So you square each of the components, add them up, take the square root. That's easy. Let's actually take a look at number 12. Okay, so we're going to look at this exercise number 12. In exercise number 12, we're given a vector. The question reads, find a unit vector. I'm going to write this as we go along. So this is in section 5.1. Section 5.1, and we're doing exercise number 12. So in number 12, a vector U is in R3, three-dimensional vector, -1, 3, 4. The question, part A, so we want to find a unit vector in the direction of U. Unit vector in the direction of U. Of the vector U. And then in part B, in the direction opposite that of U. So let's see how we're going to do this. And once we do part A, part B is going to be easy. We want a unit vector in the opposite direction of U. All right. So for this one, how are we going to do this? Well, a vector, unit vector in direction of another vector. First, let me switch to my notepad here. Okay, this one. So how are we going to do this one? The formula, remember we had a formula for the unit vector in the direction of u. Now, in the formula, it's kind of a little ironic because the formula we had was this: u is equal to vector v over magnitude of vector v, right? That's the formula we had. But here he actually switches from v to u, so I don't know. Let's use v. We're going to switch on him also. So we're going to say v. This vector v is in the direction of u. So you get the vector u over you divide by magnitude of u. And there you have that one. Now vector u is going to be what? It's going to be negative 1, 3, 4. And magnitude of u, that's when you square each part, correct? So we go negative 1 squared, 3 squared, and 4 squared. And then you take the square root of that. True, that's going to be the magnitude. And the magnitude ends up being what? 4 squared, 16, plus 9 plus 1 is 26, right? Therefore, the unit vector in the direction is going to be negative 1 over root 26. 3 over root 26 and 4 over root 26. So this is the unit vector in the same direction as vector u. Now we want one in the opposite direction. So for part B, all we got to do is just change the direction of negative v to negative v. So the unit vector in the opposite direction, therefore, is going to be 1 over root 26. True. Negative 3 over root 26 and negative 4 over root 26. This is a vector going in the opposite direction. So first we find it in the same direction and then multiply by negative. And there you have that one. Again, if you have any questions, please ask. Otherwise, we will just keep rolling. So that was number 12. Let's take a look at another one. Maybe one for distance between them, right in here, distance between two vectors. So for this one, I'm going to do number 22 here. So in number 22, we have a vector in R4. That's a 0, 1, negative 1, 2. And then the vector V is going to be 1, 1, 2, 2, 1, 1, 2, 2 in number 22. And you want to find the distance between them. So let me switch to my OQCam. There. So how are we going to do this one? Again, the distance, we had a formula. The distance between two vector UV is going to be magnitude of U minus V. Remember that one? We did that one earlier. True. Let me see if I can find it. There you go, this one. Remember we said distance between U and V, it's going to be V minus U. We want to find the magnitude of this vector. All right, and the magnitude of that vector U minus V is going to be, we just subtract vector V from vector U. So it's going to be, that's going to be 0 minus 1, right? So it's going to be magnitude of the vector, negative 1. 1 minus 1 is 0. The third component of U is negative 1 minus 2. It's going to be what? Negative 3. And 2 minus 2 is going to be 0. There you have that one. And then to find the magnitude of any vector, including this one, we square each component. And then take the square root of it, which again, sometimes I go square root. If the square root is too long, I just go to a half. That's just me. So it's going to be 1 and 9, 10. That's going to be square root of 10. That's going to be the distance between the tip of those two vectors. Okay, on that one, let's take a look at, again, please, if you have questions, folks, ask. Otherwise, I gather you're okay. Let's see if this one, finding dot products. This, we could do this one. This won't take long. Let's take a look at number 26. In number 26, we have vector u is 4, 0, negative 3, 5. And vector v, I'm writing these in my notepad here. And then vector v is 0, 2, 5, and 4. Okay, the question, part A, we want u dot v is, and in part B, we want v dot v. In part C, magnitude of u squared. And in part D, u dot v times v. Remember, u dot v is going to be scalar. So in part D, we're looking at the scalar multiple of vector v. That's what that one is. And finally, in part E, we want u dotted with the vector that's 5 times the vector v. Okay, let's see how this is going to go. Yeah, let me switch back. And there you have it. So we're doing again exercise number 26. All right, the first u dot v. Okay, u dot v. So we're going to multiply each component together and then add them up, right? So for u dot v, that's going to be 4 times 0 plus 0 times 2 plus negative 3 times 5 plus 5 times 4. There you go. And again, at this point, it's like, well, what is this number? Just think of it as multiplying two vectors. That's the best we can think of. 4 times 0, 0, 0 times 2 is 0, negative 3 times 5, negative 15, and 20. The answer will be 5, scalar 5. Okay. And in part B, we have v dot v. Remember, v dot v, that means you're multiplying vector v dotted with itself. So it's going to be 0 times 0 plus 2 times 2 plus 5 by 5 plus 4 by 4. And that's going to make it 4 plus 25 plus 16. And therefore, that's going to be 45. And just to note, that's magnitude of v squared. Remember, for magnitude of the vector, you square each component, add them up, take the square root. Because we don't have a square root, because it's just a dot product. So that kind of checks. That's going to be the magnitude of the vector squared. In part C, we want magnitude of u squared. So how do you think? See if you can help me here. In part C, magnitude of u squared. There are a couple of ways we can do this, right? One is to find magnitude of u. We have a formula for that, right? So square, 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 square each of the components of u, take the square root, and square it. And there's another way we can do this. Aside from finding the magnitude, anyone remember how we can do this without actually doing the magnitude? Using properties of dot.
Oh,
Yes, Jordan.
yeah. I think it was talking about like in theorem 5.3 for C, that the magnitude of some vector squared equals the dot product of that vector, like like the vector u dot product, the vector u.
Excellent. Fantastic. Thank you, Jordan. Appreciate it. Very good. Very good. So indeed, that's what we want to do. So we're going to do the dot product. Again, that's just an alternative to finding the magnitude and squaring it. Perfect. Thank you, Jordan. And so u dot u again, that's just going to be a vector u dotted with itself. So you multiply each component times itself. So it's going to be 4 by 4, 16 plus 0 by 0 plus negative 3 by 3 by negative 3 is 9. And 5 by 5 is 25. And that is going to make it 50. Thank you, Jordan, again. Now, for the next one, u dot v. Well, u dot v, that's from part A. That's good. We've already done that, haven't we? We've done u dot v. Right, this is u dot v. So u dot v is going to be 5. And then multiply that times vector v. Vector v is 0, 2, 5, 4. So that's going to give us a vector that is 5 times the length of this vector, right? And you multiply 5 times each component. So that's 5 by 0, 5 by 2, 5 by 5, 5 by 4. And that's the 5, really, that's 5v. That's what it looks like. In part E, it says do u dotted with 5v. Well, that's good. We just did 5v, didn't we? Because u dot v was 5. So now you're doing a dot product of u. That's, let me just write this. We're doing a dot product of 4, 0, negative 3, sorry, negative 3, 5, dotted with 5v from part D. That would be 0, 10, 25, 20. And this dot product, again, component-wise, we're going to get 4 times 0, that's 0, plus 0 by 10. 25 times negative 3, sorry, my negative 3 doesn't look that impressive. 25 times 3 is 75 negative, and 5 by 2, 10, so that's 100. So said and done. On this, please verify my arithmetic. So if everything looks good, then it should be 25. And there we have that one. So nothing earth-shattering. It's a good thing. I'm glad. So it's kind of fun doing it. It's definitely doable. So, again, assuming everybody's okay. How are we doing on time? 7:30. So we got 10 minutes before we go on for our break here. So that we can maybe squeeze in a couple of problems. How about let's take a look at how about number 40? Let's take a look at number 40. In numbers 37 to 44, so in this segment, this is where the question asks you to find the angle between two vectors. It's near the end of the section. So let's take a look at number 40. I'm gonna, well, let's do this. So again, we are in section 5.1, number 40. So I'm gonna write the vector first. Vector u is given by cosine of pi over 3 and sine pi over 3. And then vector v is cosine pi over 4 and sine pi over 4. Okay, that's kind of different. This is number 40 again. Let's take a look. Again, the question says find the angle between two vectors. So let's see how we're gonna do this. Share my note. All right. So I've written the problem here for us. Now, to find the angle between two vectors, we have a formula, right? So I'm just going to write the formula that is cosine of theta is equal to u dot v, remember this one, over magnitude of u, magnitude of v, times the magnitude of v. So that means we need to find the dot product first of all. So dot product of UV, that means cosine pi over 3 times cosine pi over 4. Uh, let's write that one. That's cosine pi over 3 times cosine pi over 4. And of course, we have exact value for those. So I'm holding off on that for a moment. Plus, we multiply the second components. That's sine of 60 degrees times sine of 45 degrees. And again, we know those exact values. If you do plug them in, that's fine. I'm leaving it for now. The magnitude of u, that's when we square cosine squared pi over 3 plus sine squared pi over 3, right? Sine squared pi over 3. And we take the square root of that, and that's going to be the magnitude. And then times magnitude of v the same way. That's when we square cosine squared pi over 4 plus sine squared pi over 4. Now this is actually quite interesting. Anyone recognizes the numerator as well as the denominator? The denominator may be easier to recognize, and then we work on the numerator. What is cosine squared plus sine squared of the same angle? That's like cosine squared theta plus sine squared theta. Does that resonate?
It's it's reminding me of, well, I don't know if it is, but it, like when I see like a cosine as sine squared, it reminds me of like the that rule thing where they equals zero, or like they equal one or something like that, but I don't know if that applies when the angles are different values.
No, you're absolutely right.
Oh, okay.
Thank you again. So this is the Pythagorean identity. Cosine squared plus sine squared, as you said, is 1, as long as they're the same angles. And that's cosine squared pi over 3 plus sine squared of the same angle. So we don't even need a calculator for this one. We can make it go a little faster. So that's just 1, isn't it? We don't have to bother with that. And what about the one next to that? Isn't that pretty much the same, isn't it? Cosine squared plus sine squared of the same angle. So that's also 1. The denominator is 1. Cool. Again, you could use your calculator, but there's really no need for this one. Now, in the numerator, let's see if we can do this differently, other than what you call it, other than um, using a calculator. Does anyone recognize the form, the structure in the numerator? And for this one, we have cosine, cosine plus sine, sine. Does that ring a bell? Cosine, cosine, sine, sine. That's actually the difference formula for cosine, isn't it? Let me write that one. This is kind of our identity corner. So the difference formula for cosine. Cosine of A minus B. Cosine of A minus B is cosine A cosine B plus sine A sine B. That's what the cosine of the difference is. And I know it's been a while. You guys probably seen this, so that's okay. Quite all right. So I'm going to actually use that little trick. Again, you're welcome to go for your calculators, but it's really not necessary. I'm just going to write it as cosine of pi over 3 minus pi over 4. There. So that was nice and handy. Now, pi over, the denominator is 1, right? So we can just forego the denominator. Just let go of that. Now, pi over 3 minus pi over 4, let's do that in this on the left side. Pi over 3 minus pi over 4. The LCD, because I'm combining fractions, I need LCD. And the LCD is going to be 12, right? So I'm going to multiply top bottom of this by 4, top bottom of this one by 3. And what are we going to get? We're going to have 4 pi minus 3 pi. That's just pi. The denominator is 12. Unless I made a mistake, that's just going to be pi over 12. So the answer is cosine pi over 12, right? So how are we going to find, um, oh, we actually found, see, isn't this cosine theta on the left side, right? That was the formula. We just followed the formula for cosine, and this is what we got. So from this last equality, can I say what theta is? Theta must be pi over 12, doesn't it? You see that? So that is the exact value, folks, without a calculator. How about that? The measure of the angle is pi over 12. Of course, this measure is in radians, right? How would I convert it to a degree if I'm interested in degree measure? We need to multiply by a conversion factor, right? And to convert from radian to degrees, we have the formula 180 degrees to pi radians, right? Divide the pi's out. So in degrees, that's 180 divided by 12. Now 180 divided by 12, that's going to be 15, right? 5 times 12, 60. So I don't have a calculator on me. Oh, 0. And there you go. The answer is going to be 15 degrees. That's the measure of the angle. So the angle between those two vectors is going to be, it's going to be that. All right. Are we okay on this work? Ladies and gentlemen, we have reached our break time here, just a minute away from it. Are there any questions? Okay, so coming out of section 1, we talked about the dot products. Pretty much that's all we did was dot product. And of course, we talked about the angle between two vectors. If the angle is 90 degrees, we said the vectors are orthogonal. Otherwise, the vectors could be going in the same direction, opposite direction in the case where they were parallel, or this simply could be theta degrees or radians apart. Now, in this section, what we want to do is now we want to extend the concept of a dot product to vector spaces. Okay, so this is now where it's different from your, if you have Calc 3, the early part of Calc 3, or if you had pre-calculus, this stuff we do now, most likely you haven't done it before. So first of all, what I have here in my notepad is the dot product that we had in section 5.1. We're going to call that dot product a Euclidean inner product or scalar product. And that's going to be like the standard form of the dot product or standard inner product. And the notation we used in that section was U dotted V. So remember, this is going to be a Euclidean inner product, standard. That's how engineers do it. This is how scientists do it, the way we defined the dot product. Now, we also have, that's not the only dot product that we can do. It turns out there are also non-standard inner or dot products as well. These are more general. So the Euclidean inner product was the standard for the industry, let's say, for engineers. And now we're going to look at the general, including non-standard inner products. Now, the notation for the non-standard we're going to use, it looks like U comma V, it looks like a vector notation, doesn't it? So I'm following the notation that's in your book. And this is the notation we're going to use. We have angle brackets and then U comma V. Now, in order for the non-standard or the non-Euclidean or general inner product to be defined, this inner product must satisfy a set of axioms. Just like the axioms we had for the vector space. Remember, we had those 10 axioms for the vector space. So this one also is going to have a set of axioms. And these axioms are going to be very similar to the axioms. We had 5 of them in section 5.1 of the dot product. Very similar to those, only for general inner products, non-standard including. So these axioms work with non-standard or general inner product as well as with the Euclidean one. The Euclidean is like a special case here. So the inner product space, therefore, is going to be a vector space V that has inner product. We call that inner product space. Okay, so now let me switch to the page of the book, and then we're going to see these definitions and we go forward. So I mentioned about the Euclidean or the inner product. So this is where you can read about it. Remember what we did in section 5.1 was U dot V. That's the Euclidean for Rn we just did before the break. After the break, we're going to generalize it. So for any general inner product vector space, for a vector space, we're going to use the angle bracket. So there's no dot here. You see that? But this means dot product, inner product, if you will, but it's for the non-Euclidean version. Now, what are the axioms? So there you go. This is the definition now of inner product. So let's say we have 3 vectors in a vector space now, vector space V, and we do have a scalar C. Okay, so what is the inner product for? The inner product on vector space V is a function. It is a function. Associates a real number to this dot product. Remember, this is a dot product. If you think of it as that, then everything here will make sense. Numbers 1, 2, and 2, 3, and 4 make sense. With each pair of vectors satisfy the following axioms. 1. Remember, in the previous section, we said U dot V equal V dot U. That's exactly the same thing, folks. So the inner product, we call it, instead of dot product, the inner or dot product of UV is equal to VU. And then this is second property. This is exactly like before. This was like U dotted with V plus W, the distributive property. This one, number 2, is called the additive axiom. The first one, the UV, U dotted V, V dot U is the same. That one is commonly known as the symmetry axiom. So we have the symmetry axiom, and then we have the additive axiom because this plus on the right side of number 2, the plus that you see on the right side. Additive axiom. Number 3 is the constant multiple, C times U dot V. Remember in the previous section, we had C times U dot V, said you can multiply C times U, or you can multiply C times V. This is often called a homogeneity axiom. Homogeneity, as in homogeneous, homogeneity axiom. And item number 4 is often referred to as the positivity axiom. Positivity in the sense that the dot product of a vector and itself, the inner product of a vector and itself is going to be at least 0. At least 0. And again, we mentioned this earlier in the previous section. The inner product is a scalar 0. The dot product is 0 if and only if you have a 0 vector. So again, if you think of U comma V, the angle brackets, as a dot product like in previous section, then these are manageable. You can think about it. Now, again, here, remember we mentioned the Euclidean inner product in the previous section. Satisfies these axioms of inner product. And so you can see this now is establishing these. Um, and pretty much these were established in the previous section. So he's referring you to previous section, Theorem 5.3. So this one, this was in the previous section. All right. Now, um, we'll do our own exercises in a moment. And by the way, look at this dot product, example 2. See this? This is not a standard Euclidean dot product. For this to be standard dot product, remember in the previous section, you multiply u1 v1 plus u2 v2, but look at this one. It has 2. So this is how he is defining this. So this is not a standard. This is a non-standard inner product, right? Now it says verify or show that this defines an inner product. So it's got to meet these 4 conditions. And he actually shows the 4 conditions. Commutative property, right? They call symmetry axiom. The symmetry axiom is there. The second one was the additive axiom, distributive property, if you will. That one holds for this. The third one was homogeneity, the constant multiple rule. That one holds. And again, we'll do our own in just a moment. I'm just briefly going over these. And the positivity axiom, you dot V with itself. So again, the way this works, when you do inner product of UV, you multiply first component, second components, you double up on the second one. So that's how you get 2V sub 2 squared. You just double up on the second product. And that's going to be positive because you have squared and you have squared of the second component. All right. And for number 4, so this is greater than or equal to 0. And it is 0 if and only if you have a 0 vector, because that's the only way v1 squared can be 0 and v2 squared could be 0, because those are non-zeros. You're squaring them. Okay. And let's see. What else? Now, in here, by the way, we'll look at an example later on. I have one that's kind of mimics this one. What I just want to refer to is the C's here, the coefficients on these products. You can think of these as weights. These coefficients are called weights. Okay, so keep this in mind, the coefficient being weights for the example I have for you later on. Now, here's an example of a function that's not an inner product. To show that it's not, kind of like on the exam. Question 1 said, does this represent a vector space? And on the exam, property number 2 was violated. So almost everybody stopped at that, said, look, it's not because it violates property number 2, axiom number 2. Same thing with this one. Of those 4 axioms, if one of those is violated, we can stop. You say it's not satisfied, therefore it is not an inner product. So here he chooses axiom 4. Remember positivity? And to show something doesn't satisfy or doesn't work, you can use what we call the counterexample. A counterexample will disprove. It doesn't prove, but it will disprove an assertion. So here's a counterexample. It says, let's do v dot v when I have 1, 2, 1. And then according to inner product definition, the dot product is defined as you multiply first one, first vector, component, first component, first component, second, second, third, third, but -2 times in the middle. So he does that, and you get -6. And remember, the positivity axiom said that any vector dotted with itself has to be at least 0. Well, this turned out to be negative. Therefore, it's not going to work. So this is not an inner product on R3, a non-standard. Okay, let's continue on. Now, this is cool. Now, this one is inner product from calculus. Okay. And For this one, it's pretty cool. I like this example. Um, suppose we have two functions f and g. C in the vector space C. Remember C bracket AB. This means the set of all continuous functions from A to B. So the dot product, the inner product FG, and he defines it to be simply product of f of x, g of x. So keep in mind in your calculus courses, for instance, when you the example, the exercise, homework, test, whatever, anytime you're doing the definite integral of something like x sine x or x squared e to the x, something like that, knowing or not knowingly, you're doing an inner product, an inner product, a dot product of those. So let's see if this, and the way it's defined, this dot, here's our dot product, is a definite integral, C, sorry, F times G. So does it meet the four axioms? Remember, the first one was commutative. FG, GF. Is the dot product of FG and GF the same? Yes, because f of x, g of x. You can switch f of x times g of x. That's g of x times f of x, right? Therefore, yes, it is, there is symmetry. It is commutative. Next one is distributive. If I do f dotted with g plus h, well, your g plus h is this one. When you dot it the way he defined it up here, you multiply the two components. So he's multiplying the two components. And then the next step, he distributes f of x to g of x, f of x to h of x. So fxgx, remember fxgx, that's f dot g. fxhx, that's f dot h. Therefore, the additive axiom holds, and that's the next line. There you go. The third one, that one was homogeneity, right? The constant multiple, C times the dot product. So how's this going to work? Well, we're going to go C times F times G. And then, so we multiply C times, first C times the integral. That's C on the outside, right in here, the way it looks in number 3. F dot G is the integral. Remember, using properties of definite integrals from calculus, it is okay to move the constant in and out of the integrand, right? Only the constant. So we're going to move this constant inside the integral. And then once we do, now you can see that C times f of x, this would be the first component dotted with gx. So that is indeed the third property, the third axiom. And finally, the non-negativity, that's f of x squared is greater than or equal to 0. So f dotted with itself, that gives you f of x times f of x, which you can write as f of x squared, right? So because you square the f of x, right? As what are we going to get here? Well, remember the positivity axiom said the dot product has to be positive, and clearly this is positive because the integrand is positive, right? Up here from calculus. If the integrand is positive, the definite integral, we can think of it as the area under the curve, right? From Calc 1, remember area under the curve? And that's going to be positive. So there's positivity. How can this integral be 0? F dot F0. Well, this can be 0. The only way this integral can be 0 is if the function, this is the 0 function, right? In the set of continuous functions. Or when a is equal to b. Now a equal b, right in here, because the integrand, remember one of the property of definite integral from calculus, Calc 1, is the definite integral from a to a. A to a of any integrand is 0. So it's saying when a is equal to b. That makes the lower upper limit exactly the same from Calc 1, that is 0. Okay, so therefore, the way this is defined, the inner product, that defines inner product. Now, the properties of dot product. So these properties now, suppose we have three vectors in the dot product space V. And again, like before, C is a scalar. The dot product of 0 vector and V gives you scalar 0. The dot product of the sum of UV dotted with W, you can distribute W to U plus W to V. This looks just like property number 2, doesn't it? There you go. Look at number 2. U comma V plus W, you distribute from the left. This one looks like you're distributing from the right. This one. And finally, this one. This one we've seen earlier. I'll scroll back in a minute. If you have C times the dot product UV, you can multiply C times V. Remember, up here, we multiplied, look at this number 3. Didn't we multiply C times U? So you can do either or. You can multiply C times U or C times V. And those are the properties here. Now, let's see. This is the definition of length, distance, and angle. The length of the vector. Again, a lot of these, folks, is easy to relate to or remember if you connect them to section 5.1, where we talked about the Euclidean inner product. So UV are two vectors in inner product space now. You see that? That's the only difference. The norm of the vector is, remember, it was U square root of U dot U. That's what this is. The distance between U and V, we had this, we did an exercise on this one. It's just like previous section. Look at the formula for cosine. The cosine of the angle is U dot V. You can think of the numerator as a dot product, inner product. So it's U dot V over magnitude of U, magnitude of V, exactly like before. The two vectors are orthogonal if the inner product is 0, scalar 0. Okay. And let's see. Let's keep going here. See what else we come across. Let's see. We'll do our own example in just a moment here. Okay. Let's take a look at this theorem, theorem 5.8. And then we'll do some examples. I think that's the last of our theorems here. And then we talked about projection too. Okay, now theorem 5.8, by the way, folks, is interesting. In the previous section, we talked about Cauchy-Schwarz inequality. We talked about triangle and Pythagorean. And there you go. All three of them are in this theorem. So suppose we have two vectors in the inner product space V. Then the Cauchy-Schwarz holds, triangle inequality holds, the Pythagorean theorem holds. All three of those that held for a Euclidean inner product also hold for a non-standard general inner product. Okay, so that's good to know. And let's continue on. This is just an example of a dot product. It's showing you're trying to calculate the work done, pulling a wagon here. The kid is pulling the wagon. So you may have seen this in physics, even in calculus classes in third semester. All right, let's continue on. Now, next work here, next segment deals with orthogonality. So we're looking at orthogonal projection in inner product spaces. So the orthogonal projection is right here. Now, if you look at the orthogonal projection, figure 12, I'm looking at figure 12 here. So here's a vector u. Okay, so the vector u is going in that direction, and 0.42. If you project, means drop a perpendicular line from the tip of the vector perpendicular to vector v, then this vector that goes from 0, 0 to 12 fifth, 16 fifth, that's called the projection of vector u onto vector v. The projection is a vector quantity. So projection of u onto v is a vector quantity. In pre-calculus, we learned, hopefully you did, because not everybody covers this in pre-calc, or even calc 3, you may have covered this. If you look at the magnitude of the projection, that means from 0, 0 to 12 fifths, 16 fifths. If you look at the length of this vector, we call that component, C-O-M-P, component of u onto v. Component is a scalar quantity, but projection, as you see, projection is a vector quantity. Okay. Now, if you look at figure 511, part A, just the projection. So here's vector u, and you have a vector v. So the projection of u, you draw perpendicular from the tip of u onto v. And this vector, projection u onto v, is going to be this boldface vector. Notice the projection of u onto v is a scalar multiple of v. It lies along in the same direction. So that's why he has a times v. A here is a scalar. So that just gives you a scalar multiple. Even in figure 12, the one I just went over, projection of u onto v is some scalar multiple of v. So for example, it could be 3/4, looks like about 3/4, well, 5/8, whatever. Whatever that distance is, the ratio of this projection to v is. But the point being, it's a scalar multiple. And let's see, how do we find the orthogonal projection? Here's the formula for projection. It's down here. To find the projection of vector u onto v. Now the notation, folks, the subscript here, you see, I'm looking at definition of orthogonal projection. If you look at the formula, the left side, it looks like the subscript on J is V. This is the vector you're projecting onto. If you change this to projection of V onto U, you get a different projection. Okay? So this is how it's found. You do the dot product of UV over the dot product of V with itself. Remember, that gives you the magnitude of the vector, right? Squared. Times a vector v. The fraction, because the numerator is a scalar, denominator is a scalar, the ratio would be scalar. So you're doing a constant multiple of vector v, which again reinforces what we said earlier, projection. That's in figure 11, that's the role A plays. And there you have that one. And again, it makes a difference what projects onto what. And to clarify this, let me show you something on my OQ cam. Okay, so we want to show that the projections are different. So suppose I have a vector here. I'm going to make one up. This is vector u, and suppose this is vector v. Okay, and I want to do projection of vector u onto v. That's what we want to do. U onto v. So how am I going to do this? I'm going to project the u onto v. Well, I'm going to extend my vector v here, right? Because it doesn't go far enough. I'm not changing my vector v, folks. That's my vector v. It's this one right here. I'm not changing that. But I need to draw perpendicular to from the tip of u onto the extension of v, if you will, right? Perpendicular. So this is actually the vector that goes from, let's say here, whatever, O. So this vector that goes from O to the projection, this is actually the projection, the whole thing, the whole thing. This is what the projection of U onto V is. You see that? Now, let's do projection of V onto U. To do V onto U, we look at V and draw perpendicular. There you go. That's the perpendicular distance. And now this vector, you see, is a whole different vector. This vector is actually projection of V onto U. Here's vector V, this is vector U. So those are different again. So it makes a difference where you place the U and V. Okay. And there we have that one. So the formula again for projection, we have a formula for it. Let me go back to the page of the book. And of course, you don't have to memorize these formulas anyway, but there you go. That's what that is. And in here again, oh, there you go. It's what we were doing, what I was doing in my notepad. So it's showing you these, let's see, what is he doing? So this is vector U, here's vector V, tip of U perpendicular to V. That's, there you go, projection of U onto V. Remember the distance from tip of this vector U to the tip of the projection, that gives you the distance between those two vectors, right? That's the distance he's talking about. And then if you look at the scalar multiple of V, whatever that is, this is now the distance between these two vectors. This is not a projection, right? What he has, the CV is not a projection, is it? Because it's not perpendicular. See, it has to be the one above is, look at the one above, look at this one. That's just the scalar multiple. Now, the orthogonal projection and distance. So we have two vectors in the inner space, product space of V. V cannot be zero because then you get division by zero here, right? Then the distance between two vectors, U and projection. So that's this one right up here. We want to find that distance. Well, he doesn't say how to find it. We'll look at that later. But all he's saying is that that distance is going to be less than or equal to the distance from U to a scalar multiple of V, as long as C, if C doesn't equal to that. Okay. I'm not sure where we're going to use this, but it's there nonetheless. Now, this is something interesting, folks. Orthogonal projection of integrals. And let me also say, a lot of what we look at with non-standard, non-Euclidean inner product spaces are really abstract ideas. They don't have geometric interpretations. Okay, just to lay that straight. We cannot geometrically, like what's going on geometrically, it's really, there's no geometry there. It's just something that's defined in abstraction and something that can be done. So for instance, look at this one. You're looking at if f of x is 1, g of x is x. You have a continuous function in the interval from 0 to 1. And here's an inner product that's defined, right? That's the dot product is the way it's defined. It says find orthogonal projection of f onto g. So what is that geometrically? Again, geometrically, that's why you don't see a geometry of this. It just is kind of an abstraction. It's really an abstract idea. So it says, okay, well, f dot g. So what is he going to do? F dot g is 1. F is 1. G is x. So he's going to do the integral from 0 to 1 of x, right? Let me transfer this onto my notepad and I'll explain what I'm saying here. Example 1. So f of x is 1. g of x is x. And we're looking at all continuous functions in 0 to 1. The inner product, I'm writing on my notepad, I'll share with you in just a moment. A to b of f of x gx, that's just how the dot product is defined. Product of two continuous functions. Find orthogonal projection. Okay. And then I'm writing the formula for orthogonal projection of f onto g. Notice we're thinking of that f and g, thinking of those as vectors now, right? The integrals as vectors. So it's going to be, I'm writing the formula down that's at the bottom of the page, g comma g. Okay. So we need to find the inner product of fg. Okay, now I'm writing still what he has, and then I'll show you how he's getting these information. Magnitude of g squared, and that's 1/3. Okay. And then this is going to be times g. And the answer he has is 1/2 over 1/3. G is x, 3/2 x. Okay, let me switch to my notepad now. There you go, folks. This is what I've been writing. So I just copied the information from the book. Now, you want to see how is he getting these half and this 1/3, right? Well, f dotted with g. F is, so here's what he's doing. The f comma g means the dot product. That's going to be 1 comma x, right? How is this dot product, inner product defined? That's the integral from 0 to 1 of f of x, g of x. So you're going to multiply 1 times x and then dx, right? The integral of x, a little bit of calculus here, simple, calc 1. That's going to be, remember the integral of x is x squared over 2. You go fundamental theorem now, upper minus lower limit. So we're going to get 1/2 of 1 squared minus 0 squared. That's 1/2. There you go. So here's how he gets this 1/2. Now let's do the integral of g. That means the dot product, inner product of g with itself. Remember, g is the x function. So we're doing the inner product of xx. That would be the integral from 0 to 1 of f times g dx. This is the integral from 0 to 1 of x squared dx. And the integral of x squared is 1/3 x cubed from 0 to 1. That's going to be 1/3 1 cubed minus 0 cubed, and that is simply 1/3 times 1. And so that's how he's getting these numbers. Now, what is the projection? This was a formula for projection. And the projection is f dotted g over g dotted g times vector g. This g is a vector. Okay, which is like, but this x, how can it be a vector? Well, think of it as an object of a vector. So f dot g, we just showed that's 1/2. That's the numerator. G dot g, we just showed that's 1/3. So that's over the third. And g, remember, g is this vector, x. So that's your g here, there. But don't put arrow on top of x, by the way, and you don't need to boldface it. I just want to make sure you see the x. So you don't have to boldface, don't put arrow. And 1/2 over 1/3, invert and multiply, you get 3/2 x. And this is what I was saying. 3/2 x, I'm trying to relate this to the geometry of this. There is no geometry, folks. So we're thinking about inner products strictly as an algebraic operation. There is no geometry here to tell you about, or I would have. So it's just, again, an abstraction with inner products, dot products. Because clearly 3/2 x, there is no geometric interpretation of projection of a function 1 onto x. Now, one thing, let's see. I'm going to try to make it into a something sensible. Now remember, f of x equals 1. That would be this line, right? This is f of x equal 1. And g of x is x. Isn't that what g of x is? X. It's the identity function, right? Running through the origin. And what we found is the projection is 3/2 x. Well, 3/2 x is a line through the origin. The slope is 1.5. And there you go. And of course, everything is from 0 to 1, right? So there you have it. This is this one. Here's this 1. And there you go. You see what I mean? The geometry of this. Not sure how this we can relate it. But so this is the x. This is 1. And this is what we just found. This was 1/3 x. You see that? So we try not to relate this to geometry. That's why you don't see in the book, he doesn't try to do any geometric interpretation either. It's simply an abstraction, is all that is. Okay, now let me go back to the book and oh, cool. That was the last thing we wanted to do. Now, let me do an example for you. And this example, again, I'm trying to reinforce. I want to remember I just said there is no geometric interpretation. We're not supposed to translate this necessarily into geometric interpretation for non-standard, non-Euclidean inner products. Okay, so here's the example. Okay, so for this example, we're going to look at we're going to look at an unusual unit circle in R2. Okay, so in fact, if you want, I can write it like that. We're looking at unusual in a literal sense, unusual unit circle in R2. Let's see what's unusual about these unit circles. First, let's take a look at the Euclidean inner product. Now, the Euclidean, there's nothing unusual about it. It's what everybody does every day. That's what you've done all your math lives, and myself included. So for this one, I'm going to sketch. You're going to like this one, folks. This kind of blows your mind away a little bit. Sketch the unit circle. Okay, so that's what I want to do. I want to sketch the unit circle in R2 in 2-dimension using inner product, dot product, u dot v. And this is how we're going to define this u dot v. It's the way we defined it in the previous section, u1 v1 plus u2 v2. Remember, that's the Euclidean version of the inner product, correct? If u is xy. Okay. And of course, we can relate this to u1, u2 as components. We think of xy as components of the vector u. So how do I find the magnitude of u here? Remember, we were in the previous section. The magnitude of a vector is going to be the dot product, which we now use the fancy notation of inner product. It's the dot product of a vector with itself, right, to 1/2, right? And that means you square the first components, you square the second component, because that's what magnitude of the vector is, right? You square the first component, you square the second component. Maybe let me put more step in here for you. So for this one, again, how are we going to do this? u1, v1. This is u1, but then times itself. This is xy. We're going to dot it with itself. So that's why I'm writing it twice, because we're about to dot it with itself. Okay. So what are we going to do? We're going to do U1, V1, that you multiply the first components. So it's going to be X times X plus U2, V2. So you multiply the second components, Y times Y, and then to a half, right? Well, X times X is X squared, Y times Y is Y squared. That would be square root, wouldn't it? Okay. So this is the magnitude of this unit vector. No, I'm sorry, unit vector. This is just the magnitude of this. Now, um, for this one, if you square x squared plus y squared, this will equal to 1, right? It equals to 1. And this is actually the equation of a unit circle, isn't it? If the magnitude is 1, you get a unit circle, right? If magnitude of u is 1, then this equals to the magnitude. So you get x squared plus y squared equal 1. And for this one, we actually get, there you go, your typical unit circle, right? This radius 1, and so the magnitude of u is going to be 1. Again, nothing out of ordinary or unusual about this unit circle. Hopefully everybody is good so far. Now, let's actually change this a little bit. So what I'm doing now, I'm actually defining a non-standard, non-Euclidean inner product. Okay, so this one, and by the way, the reason I said 1 here is because I said to sketch the unit circle up here, remember? Unit circle, that means radius equal 1. And radius is the magnitude of, we want this, we set it equal to 1 because that's what I wanted. Okay, if I said to sketch the circle of radius 2 with that, you just set this equal to 2 squared, radius 2. That would be 2 squared for 4. Okay, now let's take a look at part B. In part B, this is the part that's going to be kind of interesting. We want to sketch the unit circle. I have it in capital letters. We want to sketch the unit circle in R2. And this time, I'm going to use the weighted. Remember earlier he talked about weighted inner products? And I said, keep an eye on that weighted statement for the coefficients or weights, C1, C2, we call them weights. So this is a weighted Euclidean inner product. All right, so that's what this is. A weighted Euclidean inner product. And this is how I'm going to define the inner product now, UV. It's not going to be the Euclidean U1, V1. It's 190 U1, V1. See, those are the weights, the coefficients called weights. And this one, I'm going to go 1/4 U2, V2. The Euclidean would not have a ninth and it would not have a quarter. But with those, I have a weighted Euclidean, the non-standard one. Okay. So this time, now I can say if vector u, let it be a vector whose components are x, y now. Okay, components are x, y. And for this one, let's find magnitude of this vector. Magnitude of u, again, is going to be u comma u dot product of u with itself to a half, just like the one we did earlier. All right, just like this one. I'm doing the same thing, only with the weighted one now. Okay, so it's that to a half. And how would this work out? Well, u dotted u, so that's going to give, remember that's going to It's going to be 1/9 x times x, y times y, and you multiply the constant 1/9 times only the first or the second one. So it's going to be 1/9 x squared plus 1/4 y squared, square root of. And because I want a unit circle, that means the radius, the magnitude of this unit vector has to be 1. Now square both sides. What do we get? 1/9 x squared plus 1/4 y squared is equal to 1. Isn't that cool? This is this is kind of strange, isn't it? Does anyone recognize this equation, by the way? By any chance? X squared over 9. Let me rewrite it. Plus y squared over 4 equal 1. That's what that is.
I think, I mean, it looks like, I don't know if it's a, oh my gosh, I was just learning about these in one of my, well, reviewing them in one of my other classes, their shapes specifically.
Exactly. You were thinking about conic sections, right?
Yes, conic sections.
Perfect. Exactly. That's what it is. Thank you again. Indeed, that's the equation of an ellipse centered at 0, 0. Here's xy. The major axis is length 6 because you take square root of 9, that's 3, -3. The major axis is going to be length 6. The minor axis is going to be the length 4, right? Square root of 4 is 2. That's -2. That's the minor axis. So here's the major, the longer of the two. This is the minor. And of course, the vertices, co-vertices, and all that good stuff. But here's what's bizarre, folks. Didn't we say unit circle? Look at your unit circle. This is our unit circle. Isn't that weird? But you can say, look, that's not a circle. This is an ellipse, and there's nothing unit about it, right? And here's to blow your mind. There you go. Magnitude of u is 1. And the reason is, folks, again, because this is non-Euclidean. We're not supposed to relate it to geometry. That's just like the integral I said. It wouldn't make sense to try to say that's 1/3 x is the projection of 1 onto x. So what happens here is this. We think of circles and ellipses in this context. We think of them algebraically. That's all we think of them at this point. Remember, I said abstraction. A lot of these concepts are abstract. They really don't have geometric interpretation. So we're thinking of this non-Euclidean unit circle in its algebraic form in this context of what you see here. It wouldn't make sense to translate it into geometry. So because the norm here, because this norm, 1, not being Euclidean, so weighting has the effect of distorting the space. That's what it's doing. It's distorting that R2 space that we used to seeing through unweighted Euclidean eyes. Isn't that cool? So it's really distorting our visions. This is a mirage, what you're seeing here. This is like it's not what it seems to be. Okay, because we're trying to see this again in a Euclidean. Like you said, this is a conic section that's called an ellipse. But when we say that, we're thinking Euclidean geometry. This is not Euclidean. This is weighted Euclidean, and we've never dealt with weighted Euclidean geometries or anything like that. So if you find this a little far out, it's like, wow, this, I don't know what to think of it. It doesn't make sense. You're right. In that context, it really doesn't make sense. And that, again, you can see this. I thought this will be interesting for you to see. This is not a circle. Everybody in the world says, look, that's an ellipse. What are you talking about? Again, it's because we're thinking in context of non-Euclidean algebraically. We're thinking of this purely dot products, inner product. That's all we're thinking of. So hopefully everybody's okay on this work. As okay can be. And this is an example of, again, non-Euclidean, uh, unusual unit circle that we just looked at. Any questions about this, folks? Now we are at 8:46. I know you're all tired, but can I keep you for another maybe 5 minutes? Would that be okay? So we can look at an exercise here, if you agree to it. I know you're tired, it's late, but if it's okay with everyone, let's just take a look at one exercise and then you have a chance to kind of digest these and then you can ask questions next week if you choose to. So with everyone's permission, let's take a look at, I don't know, something that may be interesting to you. So for instance, let's show something is an inner product, whether it is or not. Let's take a look at this one. Okay, we're going to take a look at number 8, and that'll be all for this evening. So let me write number 8. This is exercise section 5.2, exercise number 8. In exercise number 8, I have the inner product, the dot product, if you will, of UV that is defined as not just U1, V1, U2, V2, U3, V3. That would be Euclidean. That would be the standard. These are non-standards, just made up. These are just imagination of the author. There you go. This is that's how I'm going to define it. Of course, we have two vectors U whose components are U1, U2, U3, and V components are V1, V2, and V3. Okay. The question, show that the function defines an inner product or dot product on R cubed. Okay, let me switch back to my notepad. All right, so we want to show it. And remember, there were four axioms that we had to do. Okay, so let's do axiom number 1. These are the axioms. So axiom 1. Axiom 1 is the dot product of UV should equal to the dot product of VU, correct? So UV, now the scalar U1, remember, the components are scalar, right? U1, U2, U3, V1, V2, V3. These are scalars, these are constants. So if I have U1, V1, commutative property of multiplication, I can write it as V1, U1. Please make sure that you write these properly so visually you don't get distracted. Make sure you track them correctly. And then 1/4 U2 V2, I can actually switch U2 V2, write it as V2 U2. And then a half U3 V3, I can swap those, right? Again, all I'm doing is commutative property of multiplication, and that's allowed. Now, this one, if you look at this inner product, that is exactly the dot product of how V dotted U would look like, wouldn't it? For V dot U, wouldn't you do V1, U1, V2, U2, V3, U3? And that's exactly what these are with the coefficients. So the first property holds. So this one, I'm going to put a check. That checks. Let's look at number 2. Number 2 was kind of like the distributive property. So we need a third vector here. On my own, I'm just going to throw in that W vector that has 3 components. We're in R3. So what we're doing is now U dotted with V plus W, right? That's the one we're doing. So how is this going to work? Well, a vector, first the vector on the left, and this is a vector on the right side. The sum vector is a vector. So left vector, right vector. How is this non-Euclidean dot product work? It multiplies components of, again, of the two vectors together, right? And then, of course, a half, a quarter, and a half are there. So it's going to do a half. First component of u times first component of the sum vector, right? That's u1, v1 kind of up here. And then it's going to do 1/4 second component of u times the second component of the sum vector. And then it's going to be 1/2 u3 times the third component of the sum vector. And there you have it. Now, the rest is just manipulating what you see on the right side. Let's see, for this one, for instance, okay, I can distribute u1. Correct? Distribute u1, we get half u1 and v1 plus 1/2 u1 w1 plus, just doing distributive property, folks, u2 v2 plus 1/4 u2 w2 plus 1/2 u3 v3 plus 1/2 u3 w3. Just a straight distributive property. Now, within each of these products, just like I did up here, u1 v1, v1 u1 is the same thing. So just swap those. u1 w1, swap that. 1/4 v2 u2, 1/4 w2 u2, 1/2 v3 u3, 1/2 v3, I'm sorry, yeah, w3 u3. I'm just swapping these, folks. I'm just swapping them. Okay. And then finally, what we can do is this. And this would be the half of v1 u1, right? This we can think of it as the dot product of uv, right? Plus the dot product of u and w, right? Remember what UV is going to look like? This is going to be your UV. The dot product of UV is half V1 U1. There it is. 1/4 V2 U2. There it is. 1/2 V3 U3. There it is. So in other words, I am grouping this one, and this one together. That would be U dot V, the inner product. And then this one, and this one is the dot product of U and W, UW, components. And there we showed that one. Let's do number 3. Number 3, so C is a scalar now. Let's do C times U dotted V, U dot V. Okay, so for this one, that means C times the definition of dot product. He gave us that. I'm just writing it from the first line. U2 V2 plus 1/2 U3 V3. That's up here. Okay, and what do we do next? We can actually move C, because it's a constant. You can multiply it times 1/2 or multiply it times U1 or times V1. So I'm going to go 1/2 C U1, right, times V1. That's how I want to distribute it, multiply it. We're doing the associative property. We're changing the order of multiplication here. Okay, and the one next to that, what is this going to look like? It's going to be plus 1/4 multiply C times U2, and then times V2, and then the half multiply C times U3, and then times V3. Okay, and what is this one? This is simply the dot product of CU with V, right? First vector, vector on the left, vector on the right. So that's the first component of vector on the left, first vector on the right. Again, that was the very definition. So on and so forth. That's number 3, so it checks. I didn't put my check marks. There you go, check, check. And number 4, the last one for the evening. Item number 4, it was v dotted or u dotted with itself, doesn't matter. A vector v dotted with itself. Remember, this has to be at least 0. So when you multiply or do a dot product of v dot v, so you're going to get 1/2. You remember u1 v1? So that's just v1 v1, v1 squared. Plus a quarter, u2 v2. It's going to be v2 v2, v2 squared. And finally, plus a half, v3 v3, that's v3 squared. Now this one, would you agree that it's positive? Greater than 0, because v1 squared positive, positive, positive. The sum is positive, right? And the only way is 0 equals 0, and it's equal to 0 if and only if vector v is the 0 vector. There's no way the sum can be 0, right? The only time this sum is 0 is if v1, v2, v3 are 0. Hopefully everyone agrees with that. And if that's the case, that means v is the 0 vector in R3, right? There you go. That's what this is saying. Therefore, check on number 4. And so this defines an inner product in vector space V, the way they defined it. And so any questions about this work, everyone? Let me stop recording